Okay, it's time for our second talk of the day. We have Hitesh Gakhar, who will be talking to us about a theoretical analysis of quasi-periodicity using persistent Kunneth formulae.
Thank you, Altaman, for the introduction. I'm very, very excited, to be here, in my home office. All right, so I'm gonna begin my talk with the motivation for sliding window embeddings. So our story starts with a dynamical system, which is essentially, a manifold or with a diffeomorphism, and an observation function, which is, a real or a complex valued function on the manifold. If we take, say, a point on the manifold and we keep applying, the diffeomorphism onto it, we get an evolution of this, so-called initial state. And if we apply the observation function to this evolution and choose a nice temporal resolution, one can define, define or derive a time series that observed from this, dynamical system. So to summarize what I just said, given a dynamical system, an initial state, and an observation function, one can get a time series. The question is, can we get back some information about the original dynamical system if we're given this time series that we are assuming has come from, a dynamical system? And now this question was answered in the early 1980s by Florence Tarkins, and Tarkins' theorem essentially said that yes, you can. That if you have a compact m-dimensional manifold, and if phi is a diffeomorphism, f is an observation function, both at least twice continuously differentiable, then it is a generic property of the pair phi f that this vector valued function on the manifold given by this vectorization of the observation of the evolution of any x gives us an embedding. In other words, if we have a time series that has been derived from a dynamical system, then we can use the Tarkins diffeomorphism to reconstruct something that is diffeomorphic to the original dynamical system. Now this, for the purpose of time series, motivates the idea of sliding window embeddings, also known as time delay embeddings. So for a real or a complex valued function f, an integer d, which we call the embedding dimension, and a real number tau, which we call the time delay, the sliding window embedding of the function f at a point t is given by this vector. So we take a window of size d tau starting at t divided into d subdivisions, evaluate the function at each of the points and vectorize them, and hopefully you can see the parallel between the Tarkins diffeomorphism and the definition of this embedding. Okay, so the first results, using a sliding window embedding and persistence came out like a few years ago, and the first paper was by Jose Pereira and John Harrow, and they studied periodic functions in their in a very general sense. They only required the function to be continuously differentiable. So once you have like a continuously differentiable periodic function, it has a Fourier series that converges to it pointwise. And once you have like this infinite series, you can use a truncation parameter z to write these Fourier polynomials that converge pointwise to this infinite series and equivalently to this function f. So for any given z, we can choose my embedding dimension and my tau appropriately, and that and that gives us that the sliding window embedding of this Fourier polynomial is always homeomorphic to a circle, but the circle will be wrapped around a torus of dimension z. Let's break this down. So just by definition, this is what my sliding window embedding of SZF is. I've just used the definition here, nothing more. Observe, or I guess take it on faith here, that we can actually factor this into this matrix omega times this vector phi of t. And one of the conditions for the structure theorem that Pereira and Herrera came up with was that if D is at least 2Z, then this omega acts as a homeomorphism. In other words, if you have a collection of points phi of t that form a continuous space, and you apply omega on it, the topology under this process omega does not change. The geometry, of course, will, but the topology doesn't. Now, the idea is that we can, if we want to study the sliding window embedding, and if omega is a homeomorphism or a diffeomorphism, we can instead study this vector phi, because it's a lot simpler to look at, and if the topology isn't changing, then it gives us a lot of information there. But we can study this vector equivalently by studying this vector of the argument. It's the same as going from like a circle to the interval 0 to 1 modulo 1, or 0 to 2 pi modulo 2 pi. So let's look at an example and see what I mean by this. If I have a periodic function, e to the I t plus e to the I 3t, its vector of arguments, as I said before, is going to be t3t. Now, as I vary my t, like this vector wraps itself around this 2 torus, this flat representation of a 2 torus, 3 times along the meridian, 1 times along the longitude, or vice versa, whichever you prefer. And that's exactly what the theorem said, that you have a circle that's wrapped around like a 2 torus. Now, if I change this function slightly, say 3 to pi, I get the vector of arguments t comma pi t, and as I vary my t now, we don't get a closed loop anymore. In fact, this varying vector fills out the entire 2-dimensional torus. In fact, it's actually dense in it. Now, this function on the right is an example of quasi-periodic function, which I define now. So, function f is a quasi-periodic function with a given vector of frequencies omega 1 through omega n. If there is a continuous multivariable function to this particular straight line in Rn, gives us the little f. And if we fix any n-1 variables, and we look at that jth marginal function, it's 2 pi periodic, and the set of these frequencies that form this vector on the top are linearly independent over the space of rationals. There's one more technical condition, that if n is as little as it can be for a given f, then f is called a parent function. Like, we just require that to avoid some non-uniqueness problems, but I'm not going to go into that. Okay, so quasi-periodicity is essentially everywhere. It has been studied in all forms of sciences. There is it has been observed in solid state matters. It has been observed in climate change patterns, in neuroscience, and even in motion of heavenly bodies. Okay, so there's a lot of results, of course, in the paper. I can't talk about all of them, but one of the things I want to talk about is the structure theorem. So our strategy was essentially the same as the original paper, that we wanted to approximate it with a Fourier series. So if we assume enough regularity on the quasi-periodic function, and by that I mean it's at least r times differentiable, where r is at least n over 2, where n is the number of these linearly independent frequencies. Then we get this Fourier series decomposition that we see here. And once we have a Fourier series decomposition that converges pointwise to the function f, then we can introduce a truncation parameter and we again, like before, we get these sequences of polynomials that converge to the function. And so now for any given z, we want to choose the embedding dimension and time delay. So we choose the embedding dimension to be at least 2z plus 1 to the n. And we want to choose tau that makes that matrix omega as close as possible to an isometry, or at least, like a multiple of an isometry. And structure theorem essentially says that the sliding window embedding of this function SCF is going to be homeomorphic to an n torus, which is further somehow wrapped around a d plus 1 dimensional torus. Now, like this density in Tn, so yeah, I guess one comment I want to make here is that like when we go from those vectors, those collection of vectors phi to the sliding window embedding point cloud, d is enough to preserve, for most part, d is enough to preserve the topology of the underlying space. We need tau to preserve the geometry as much as possible, because even though when we compute persistence, even though we are computing homology, like persistent itself like heavily depends on how the data is laid out, like so or the geometry of the data. Okay, so let's look at an example that we'll work with for the rest of the talk. So say we have this time series that has been derived from this this dynamical system on the two torus. It's an irrational winding, similar to the example that we saw a few moments ago. We computed sliding window embedding for appropriate traces of d and tau. My d is 1 and tau is pi over square root of 3 minus 1. And the point cloud that we get is it's in 4 dimensions. We use PCA to view it in 3, and it very much looks like a torus, and persistence actually verifies that as well, and very neatly. Okay, so great. Like it does what the theorem says it would. The next question here was, do we do this faster or better? And the answer, is yes. Spoiler alert, I guess. So for this, I would need a persistent Kunneth formula that we wrote a couple of years ago. And before I get to that, I want to review the classical Kunneth formula in algebraic topology. So if x and y are topological spaces, the classical Kunneth formula allows us to write the homology of the product space x times y in terms of the homology of x and the homology of y. So in algebraic words, this short exact sequence splits, and therefore we can write the middle term here as an isomorphic sum of the tensor and the torr parts. So we wanted to do something similar for persistent homology, and we came up with two notions: a categorical filtration and a tensor filtration. I'm only going to talk about the former here. So the categorical product is essentially a product filtration where at index d we just have xd times yd. So we are taking index-wise products, and that's our filtration. We call it the categorical product because it's it's the product in the category of filtered topological spaces. And like before, we wanted to write the persistence. Sorry, like in the classical case, we had homology of the product written as or in terms of homology of x and homology of y. We wanted to do something something similar here. So we wanted to write the persistent homology or the barcodes of x times y in terms of the persistent homology or barcodes of x and y. And that's what we ended up doing. We got our theorem essentially says that if you know the barcodes of x and the barcodes of y in all dimensions, then you can explicitly exactly compute the barcodes of x times y in each dimension. Okay, now before we go before we move to time series, I just want to show this toy example. So on screen we see this the simplicial filtration of a circle. If I square it using the formula, using the definition that I just showed, we get the simplicial filtration of a 2 torus, and the numbers represent the indices at which these simplices appear. And the fact that this is a filtration of a 2 torus is very neatly reflected by the barcodes as well. 2 one-dimensional classes, 1 two-dimensional classes, or 1 two-dimensional class. Okay, so let's go back to time series. So what I want to do now is I'm going to show 2 observations, for the lack of a better word, or 2 ingredients if you like, and then using those I want to create an alternate strategy for quasi-periodicity detection that leverages this Kunneth formula, and then I will show that it actually performs better than the more standard approach of sampling out like a landmark. Okay, so observation 1. If I have metric spaces X and Y, and if I have a RIPS complex at a scale epsilon, which is the collection of all finite subsets of X with diameter less than or equal to epsilon, and if I take this, if I take the Cartesian product of X and Y and equip it with this maximum metric, then the geometric realization of the RIPS complex on this product space is naturally homomorphic to through the product of the geometric realization of these individual RIPS complexes. And because it's natural, as epsilon varies, we end up getting that the barcode of the RIPS complex of this product metric space is the same as the barcode of this categorical product of the RIPS filtration, and we know how to compute the thing on the right. The second observation is seemingly more obvious, but it just needs to be said out loud, and it's this. So the sliding window embedding, as we saw earlier, can be factored into our matrix omega and my vector phi of t. Now, if we take a large enough or an appropriately chosen set of timestamps here, each phi of t is like a 2-dimensional vector, and you can take projections in either of the complex coordinates. So if I choose this large enough t, I take projections in both the coordinates, and then I take the Cartesian product back. This new Cartesian product of pi1 phi and pi2 phi is in the same ambient torus as where phi was. As I said, seemingly obvious. Okay, now to the strategy. So we did experiment using 2 different strategies. The first is more direct and more common. You have the sliding window embedding point cloud. Theoretically, it has infinitely many points, and we can't compute persistence on that. So we need to find a landmark set, a subsample of it that approximates the truth, the ground truth really well. Then we compute the RIPS filtration of it on it, and we get like a collection of barcodes or persistence diagrams. The other strategy goes as following. So we choose like a large enough set of timestamps. We compute the collection of vectors phi on it. We take a projection in both the coordinates. We compute samples there, and then we take the Cartesian product back. That's my X times Y. We equip it with the maximum metric. We compute the RIPS filtration on it. Now, from observation 1, it will have the same barcodes as the barcodes of the categorical product of Rx and Ry, and we know exactly how to compute that by the Kunneth formula. So using these 2 strategies, we have arrived at 2 different sets of barcodes or persistence diagrams. Now, one must remember that, of course, they are very different persistence diagrams that we get, but neither of them are the actual ground truth that we cared about. They're both approximations to what we really want, right? So as it turns out, this approximation by the Kunneth strategy is actually better, and like I say so with my my faith in theoretical bounds. Right. So results. I feel like I'm almost out of time, but this is the last slide. So at first, I would like to point your attention to the bottom of the screen, the timetable. So the landmark strategy or the direct strategy took about 15 seconds to be executed. The Kunneth strategy took 0.2. So it's significantly faster. And since we were talking about approximation, I would like you to focus your attention to diagram 2, because it's a little easier to explain. It's a little simpler, but the same thing happens in diagram 1. So the blue point and the blue square correspond to the landmark case or the direct case, and the red one correspond to the Kunneth case. The points themselves at the center of these rectangles are the experimental persistence points that we get, and the boxes around them are the confidence regions where we expect to find the persistence of the ground truth, again computed theoretically. So the reason I say that the Kunneth strategy does better is because the area of this red strip is roughly half than the area of the blue square, and the other is that on an average, this red square, this red rectangle is farther away from the diagonal than the blue square. So it approximates, like the homology of a 2 torus a lot better. And in fact, the confidence region is much smaller. So it's also closer to the truth on speaking on an average, of course. And with this, I would like to end my talk. Thank you.
Please unmute yourself and applaud for the speaker. So great talk. Are there any questions for Hitesh?
Hitesh, do those computational experiments run pretty fast, or were they quite a lot of work to generate?
Which ones?
The ones at on the last prior slide.
Oh, so the experiments for the landmark sets were like 15 seconds, and for the Kunneth strategy it was like 0.2 seconds.
I see.
So like they were both fast, but yeah, they were both fast, but the Kunneth strategy, of course, was a lot faster.
Yeah, definitely. Thanks.
So I have a quick question.
Go ahead.
What is between the landmarks and the Kunneth strategy? Is there a geometric intuition for what each one is seeing?
What do you mean?
So you noted that they're both approximations of something that's not computable.
Yeah.
But maybe a bit of an explanation of what, maybe geometrically, how does this product approach differ from the landmark approach? How would the sequence of spaces that you're reconstructing for either approach compare to each other?
So the landmark approach is very, so the landmark. So you have this infinite. You essentially have, say, a 2 torus, at least in this example, like a proper solid 2 torus, or like up to the notion of like a closure or denseness. You have this you have infinitely many points there. You can't compute persistence on that. So a landmark strategy would be carefully choosing out points on that torus, and then using we can compute the house of distance between the landmark and between like a solid 2 torus or something dense in it, because it's the same, because something, if the the sliding window embedding and the torus, or the sliding window embedding point cloud and the torus will have zero host of distance because of denseness. So we can compute this distance from the landmark set to that, and that gives us bounds like on how far the persistence diagrams can be. But like now what we're really computing here is we are building Rips complexes on this approximation of this like the solid 2 torus, or like this set dense in the solid 2 torus. The Kunneth strategy, it's hard to describe. Like geometrically, I would say we're not computing Rips complex for the sliding window point cloud directly. We're taking like that vector phi that we had earlier, and we're using that to compute Rips persistence on it, and then we are using properties of omega to find these bounds. So like it's related, of course, to the sliding window embedding using that via that operator phi, but it's not like we're not directly computing anything that is sliding that is a part of the sliding window embedding point cloud. Does that answer your question? I'm not 100% sure.
Kind of. So does this strategy work? In other words, I'm trying to have an intuition for when this Künneth formula can work. So is it here that we have a torus it's somehow very, very symmetric, so that the data set is naturally can be written as a product in this way? And so the strategy works. Could it work for maybe less symmetric kinds of data?
I'm not sure, and because I would like to think of this like the strategy at least that in the form that I showed as a preliminary version of what we want to build on top of it. So like right now we only have it for toy examples, and like very, very nice toy examples as we see, but we're hoping that we will be able to build something like for more general functions.
Interesting. Thank you for the answer.
Right.
Hi, Hitesh. I just have a quick question. On the next slide, the table. I'm sorry, it's a naive question, but in the Kunneth column, why are there more points than the landmarks column?
That's a very good question. So we started. I can't remember how many points we started with, like with the timestamps. So if I'm to look at the strategy here, we started with a large number of timestamps here, and then we took projections. I think it was 4,000 points. Started with 4,000 points in both the coordinates, and then we took like 70 subsamples each, and then we took the Cartesian product. So 70 times 70, we get 70 squared. So that's why 4,900 points. And it still like does a lot faster.
Thank you.